Here we introduce a very important equation for fluid physics. That is Bernoulli's equation. Now, Bernoulli's equation has three parts to it. The pressure of the fluid plus 1/2 times the fluid density times the speed of the fluid squared plus the density of the fluid times acceleration due to gravity times the height of the fluid must be a constant. So the three different parts to Bernoulli's equation is the first one is just the pressure of the fluid. Again, that's how hard the molecules of the fluid are pushing on the walls of their container or one another. This second one you can see kind of looks like kinetic energy, right? Kinetic energy is 1/2 mv squared. This is 1/2 rho v squared. So instead of mass, we use density. This is a kinetic energy component of Bernoulli's equation. And the second piece kind of looks like potential energy, gravitational potential energy. Instead of mgh, which we use for gravitational potential energy, we have rho gh. So Bernoulli's equation really does come from the similar type of arguments for conservation of mechanical energy. That the energy in the system has to be conserved if you're not putting new energy into the system or taking energy away. So the pressure plus this kinetic energy form of the density plus this gravitational potential energy form of the density must be equal to a constant. Which means that in any pipe system, imagine the pipes coming from the water tower to your house, at any point in that system, when you add up all these things together, you have to get a constant, which means that the pressure at some point 1 plus the speed, 1/2 rho speed 1 squared, so the speed of that object, or sorry, of the fluid at that point, plus the height of that object of the fluid at that point, has to be equal to those same values at some second location. So you can keep on examining different points along the pipe, and when you sum these three terms together for the conditions of the fluid, what is the pressure at that point, what is the speed of the fluid at that point, what is the height of the fluid at that point above some reference height, those all have to be equal to the same number at all points. So this is a very powerful equation, and we'll talk about, our whole plumbing system is based on it. Airplane flight is based on this, and so on. There's a lot of important things based on this Bernoulli's equation. So let's look at two special examples. The first example is, what if the fluid is static? What if you just have water in your pipes and that water is not running? Well, if the fluid is static, then the speeds in the pipe, both before and after, are 0. So this equation reduces down to the pressure at point 1 times rho g h, the height at point 1, is equal to the pressure at point 2 plus rho g, the height at point 2. Now rho is the density of the fluid. We're assuming an incompressible fluid, so the density won't change between those 2 points. And the acceleration g is the acceleration due to gravity on Earth's surface. That doesn't change either. So you get a special case for the pressure changing with height. So at a larger height, for this equation to balance, let's say h1 is ground level, so the height is 0. Let's say this is 30 feet up or 100 feet up. What's going to happen? Well, the pressure has to change too. So when h is small, the pressure is large. When h is large, the pressure has to be small. That's one of the reasons in hotel rooms, the higher the building, the lower the water pressure is, up to a point. Hotels usually have to install water pumps in their facilities or store water on the roof to make sure they have adequate pressure. Now, for constant depth, where the height doesn't change, the rho gh are the same on both sides, so that term will cancel, and you'll end up with the pressure at point 1 plus 1/2 the density of the fluid times the speed of the fluid squared at point 1 is equal to the pressure at point 2 plus 1/2 the density of the fluid times the speed of the fluid at point 2 squared. So what does that mean? Well, this actually helps with airplane wings. So this is the cross-section. The blue here shows a cross-section of an airplane wing. An airplane wing is a specially designed system where when air hits the front of the wing, it can either go above the wing or below the wing. If it goes above the wing, it actually has a larger path to take, a longer path to take to get to the end of the wing than if the air goes below. Which means that for the air to meet up, the air along the top of the wing must be traveling faster than the air on the bottom of the wing. So V1 is greater than V2 in this case. The air above the wing is traveling at a faster speed than the air below the wing. Okay, great. What does that mean for our equation? Well, if V1 is greater than V2, P1 has to be smaller than P2 for this equation to balance. So the pressure the pressure on the upper part of the wing pushing down, is smaller than the pressure below pushing up. This is what creates the lift in aircraft wings. And it depends, you can see it depends on the speed squared. That's one of the reasons aircraft wings need to be, aircraft need to be traveling at a fairly high speed to get a strong lift to lift themselves off the ground to overcome their gravitational weight of the object. Or you need objects with just really, really, really large wings. So you have the gliders that are now famously going around the world with incredibly large wingspans to provide the lift necessary at low velocities in order to overcome Earth's gravity. So Bernoulli's equation is an incredibly important equation in physics for fluids.